Alright, today we're going to look at functions. We're going to start by looking at real numbers and the breakdowns of them. We have rational numbers, which are decimals and fractions. The decimals need to be able to be written as a fraction in fraction form. Irrational are all of the decimal numbers that cannot be written as fractions. So irrational numbers would be square root of 3, square root of 2, pi, those numbers that are ongoing forever decimals. Integers are your positive and negative whole numbers. Whole numbers are your 0, 1, 2, 3, so they have positive value, and then your natural numbers are your counting numbers, so 1, 2, 3, 4, and so on from there. And this diagram shows how they, all real numbers, and we have our irrational numbers, our rational numbers, and then integers, whole numbers, and natural numbers, and how they're subsets of one another. We're going to start by looking at set builder notation. So in set builder notation, this is written where we have x, and we're looking at all of the x values here that are between negative 3 and 10. So here, x can be negative 3, negative 4, and so on. And we're going to have x define x, and then see if we look back as all integers. So x is going to be all of the integers between negative 3 and 10. So applying that, if we have we have 8, 9, 10, 11, and so on, dot, dot, dot. We can write this in set builder notation as we're looking at the variable x, and x is going to be everything greater than or equal to 8. And then we can look at this, someone might look at this and say, oh, it's natural numbers, whole numbers, integers. We're going to say that it is integers, because we don't know if it's, we want to be as inclusive as possible. So we're going to say this is a set of all integers. Another example, we have x is greater than 7. Writing that in set builder notation, we have the set of all numbers x, where x is less than 7. And so we're going to define this as all real numbers, because this information doesn't tell us if we're just dealing with whole numbers, natural numbers, and so we're going to include as much as possible. So x is in the set of real numbers. Alright, last example, we're going to look at all multiples of a number. So all multiples of 5. So in set builder notation, we have the set of all numbers x such that x equals 5n, where n is going to be, in this case, we're just going to look at integers. We're not going to do real numbers because we don't want to include the decimals, because those would not be multiples that apply. We're looking at 5, negative 5, 10, negative 10, negative 15, and such. Now we're going to look at interval notation. So interval notation uses parentheses or brackets. Parentheses are when we're looking at if the number is like greater than or less than but does not include, and then brackets would be less than or equal to, greater than or equal to, when we include that actual point. So our first example, we have negative 5 is less than or equal to x, which is less than 10. So putting this in interval notation, since this is less than or equal to, we're going to use a bracket. So we have a bracket around 5, and then our maximum point is 10. And since it's less than 10, we're going to use a parenthesis because we're not including the actual point of 10. So we can look at x is greater than or equal to 7. So looking at this, our lowest point is going to be 7, since x is greater than or equal to. So we're going to do a bracket because we can equal 7. And x is greater than or equal to 7, so we can keep on going to infinity. And since infinity has no end, we use a bracket because we'll never quite reach there. All right, and the last one we're going to look at is a union. So we have x is less than or equal to 10, or x is greater than 5. Actually, we're going to do x is less than or equal to negative 10, or x is greater than 5. That makes better sense. So here we have all of the values less than negative 10, or a solution set could also include all the values greater than 5. So setting this up, I'm going to have a part for this piece and this piece. So x is less than negative 10, so I can have all of my negative values. So I'll have negative infinity up until negative 10, and since this is less than or equal to, I'm going to have a bracket. And then for my x is greater than 5, my lowest point is 5. That's going to be a parenthesis because I'm not including the actual point of 5. And I'm going to go on to positive infinity. Now my or, I'm going to put a union symbol. So I have negative infinity to negative 10, and then with the union of the interval of 5 to positive infinity. Now we're going to identify relations as functions. Relations are any grouping of a set of data, and then a function is when it's a special type of relation where each input has a unique output. So every time we put 2 into an equation, we should only get one answer. So let's identify a function. So the input x is a student ID's number, and the output value y is a student's score on a physics exam. Since each student should have a unique number, each student receives 1 grade on the physics exam. So student ID, student score. So each student has 1 score, so this should be this would represent a function, because no one student's going to have two test scores. We're looking at a table. This would represent a function, even though we have negative 10 is providing an output of 5, and negative 5 is also producing that same output of 5. Each one is unique. Each input has a unique output. So this is a function. This one, since 3 is giving it, when we input 3, we get 2, and we also get 4. This is not a function because we have input going into the process, into the function, and into the relation, and it's producing 2 different outcomes. So this is not a function. Looking at equations, we have 3y plus 6x equals 18. If we can solve this for y, we get y equals 6 minus 2x. This is a function because whatever values we put in for x, we're going to get a unique output here. Now, an example of an equation that is not a function would be a square root equation. And so if I have y squared equals 3x minus 7, I need to square root both sides. So I have y equals plus or minus the square root of 3x minus 7. So that plus or minus, I'm going to have two different results for every input here. So this is not a function. All right, so now we're going to look at function values, so evaluating a function. So if we start with the function 2x plus 3, and I have f of 12, I'm going to plug, since this value is being substituted in place of x, this is saying that x equals 12. So 2 times 12 plus 3, 24, 5 times 6 is 7. So f of 12 equals 27. We can also substitute, we can also put 6x here, and that's saying that our x value equals 6x. So using the same equation here, so every place where there's an x, I'm going to put 6x. So simplifying, I have 12x plus 3. So f of 6x equals 12x plus 3. And then for this last one, I can say f of negative 3a plus 8. Since negative 3a plus 8 is being substituted for x in our function, I'm going to do the same side over here. Now I need to do algebra to simplify. And I get negative 6a plus 19. So f of negative 3a plus 8 equals negative 6a plus 19. So now we're going to look at domain and range for different functions. So for our first function, we have f of x equals 5x minus 2 over x squared plus 7x plus 12. So what's going to, looking at this, we can plug in any value of x. But if we look at our domain, when we have a fraction, our denominator cannot equal 0. So x squared plus 7x plus 12 cannot equal 0. So we do not want the values of x that's going to make our denominator 0. So we need to exclude those. So simplifying this, I need to factor. I need two values that when I multiply them together, I get 12. But those same two numbers, when I add them together, I get 7. So I have x plus 3 and x plus 4. So solving, I get x equals negative 3 and negative 4. So in this case, I need to exclude from my domain the values of x of negative 3 and 4. So writing this I can write it as all real numbers except negative 3 and negative 4 in set builder notation. I have